We're going to continue with Chapter 8, covering Sections 5 and 6, which talk about the conservation of mechanical energy, and we're going to look into some graph interpretation in the last bit. Okay. All right, so conservation of mechanical energy. It's the principle of conservation of energy we've seen in other classes like chemistry. But as far as mechanical energy goes, it's going to say that an isolated system where only conservative forces cause energy changes, the kinetic energy and the potential energy can change, but their sum, which is the mechanical energy, and we're going to use E with the subscript of EMEC, of the system, cannot change, right? So basically what it's saying is the total energy, or the total mechanical energy, cannot change. So the mechanical energy of a system is the sum of the potential energy and the kinetic energy added together, right? So our mechanical energy is just going to be our kinetic energy plus our potential energy. All right, and if this value cannot change, we can see that our change in potential then must equal to our our change in kinetic must equal our negative change in potential, right? So as you increase your kinetic energy, or as you speed up, basically, you're going to be decreasing the amount of potential energy, and vice versa. All right, and we've also seen this before. Our potential energy is equal to the opposite of work. So we have that our kinetic energy is then equal to work, right? So when you're doing work on an object, you're giving it kinetic energy, you're giving it energy. So the sum of, it goes to say then that the sum of the kinetic energy and the potential energy for any state of the system is going to be equal to the sum of the kinetic energy and potential energy at any other state in the system. Now again, this is for conservative forces. So this is excluding anything like friction or anything that's going to be giving off heat or any loss of energy. All right. So in general, our equation for the conservation of mechanical energy is going to be the change in mechanical energy is equal to the changes in your kinetic and plus the changes in your potential, and that equals 0. So again, as kinetic energy increases, you're going to have the same amount of decrease in potential and vice versa. All right, so let's look at a pendulum. Let's look at an example here. The pendulum swings back and forth. During one full cycle, the values of the potential and kinetic energies of the pendulum Earth system vary as the bob rises and falls, but the mechanical energy of the system is going to remain the same. The mechanical energy can be described as continuously shifting between kinetic and potential as we go between the stages. So, for instance, let's start up here at the top. All right, so in this picture, all of the energy is going to be kinetic, and you can see the little bar graph down here that shows you where the energy is, right? Because it's at its lowest position. So as it's fallen down to its lowest position, it's going to have the most kinetic energy. It's going to be, which means it's going to be going the fastest. It's going to have the fastest velocity. Now, as you travel up, you're going to be increasing its potential, right? Because you're going further away from the Earth, so you're increasing the potential energy, and that's going to cause the kinetic energy to go down. And then you get to a point where it's at the very top of its path. So this is as far as it can go up with the amount of energy that it was given. And you're going to have a moment of zero velocity, right? So zero velocity means that there's going to be zero kinetic energy, and that all of its energy is going to be in potential. Now, as it's going back down, it's going to end up with the velocity going in the other direction, but your kinetic energy is going to be split with your potential as you go halfway down, and then you get down to the bottom, and again, it's back to all kinetic, right? And as you continue around, you kind of see the same kind of process. So if the swinging involved a frictional force, then the mechanical energy would not be conserved, and eventually the pendulum would stop, right? So if there was some sort of friction, maybe air friction in the bob, or maybe some friction up here in the string, you would get some loss of energy. Okay. So let's do an example problem. All right, so in the figure, a child of mass m is released from rest at the top of a water slide at height h is equal to 8.5 meters above the bottom of the slide. Now, assuming that the slide is frictionless because of the water on it, find the child's speed at the bottom of the slide. All right, so there's a couple of things we need to consider. First, that the total mechanical energy at the very top of the slide, which is up here, is going to be the same as the total mechanical energy at the bottom of the slide, which is down here. So we cannot find her speed at the bottom by using her acceleration along the slide, as we might have in earlier chapters, because we do not know the slope or the angle of the slide. However, because the speed is related to her kinetic energy, perhaps we can use the principle of conservation of mechanical energy to get the speed. Then we would not need to know the slope. So also, mechanical energy is conserved in a system if the system is isolated and if only conservative forces cause energy transfers within it. So the forces, well, the two forces acting on the child, the gravitational force, which is acting down, right? Which is a conservative force. It does work on her. And then the normal force on her from the slide does no work because its direction at any point during the descent is always going to be perpendicular to the direction in which the child's moving, right? So gravity's pulling her down. The normal force is always going to be at some angle, but it's always going to be at 90 degrees to her displacement. So the work done is zero, remember, because work is equal to F dotted with D. So this is F d cosine theta. If cosine is 90, this whole thing is just going to be 0, so there's no work done. So we don't need to worry about the normal force in this case. Okay, so let's start with a couple things. Let's start with the mechanical energy, right? Our equation for mechanical energy, or the conservation of mechanical. And basically that says is our energy before is going to be equal to our energy after. Right? And this top part I'll call before, and this bottom part I'll call after. Okay, so what that says is the sum of our kinetic energy before and our potential energy before is equal to our kinetic energy and potential energy afterwards. Okay, well, we know the equations for each of these, so we'll go and plug that in. So we know that kinetic energy is 1/2 mv squared. And we know that our potential energy, in this case, we're talking about the potential energy due to gravity, so that's just going to be mgy is equal to 1/2 mv squared plus mgy, right? And this is going to be before, and this is after and after. Okay. Well, one thing we can do right off the bat is we notice that every term in this equation has the mass, and we're not actually given the mass, so we would assume at some point it's going to cancel out, or we'd have to include it in the answer. So every term has m, so we can just cross out all the m's and they go away. All right. And we're trying to find what the velocity is at the bottom, right? We're trying to find this VA here. So what I'm going to do is I'm going to solve this equation for VA. And skipping the algebra, we get to our velocity squared is equal to our initial velocity squared plus 2g, and this is just going to be our y's subtracted from each other, right? Our change in height. Okay, well, we know that initially she starts at rest, so this term is actually just going to go to 0, right? And we're trying to find this VA, so let's get rid of the squared. Oops. So this VA, which is our speed at the bottom, is just going to be the square root, our square root of 2gh. And this change in height here is h, right? So this is just equal to h, right? Because you're going from some height down to 0. Okay, so at this point we can go ahead and plug our values in. So we have the square root of 2 times 9.8 meters a second squared times our height, which is just 8.5 meters. Okay, and we get a value for the velocity of 13 meters a second. Okay, so this is telling us that the velocity at the bottom of the slide is going to be 13 meters a second. And actually, if we solve that, for if the child was just falling straight down from 8.5 meters, we would get the same value. We would get 13 meters a second. All right, so let me show you a different way that we could have solved this. Coming back up to this original equation here, we know that at the top she doesn't have any kinetic energy because she's not moving at the top, right? So really this first term, I'm just going to rewrite it real quickly. So this first term is going to be 0, right? There's no kinetic energy at the very top of the slide right before she starts going down. We also know at the very bottom of the slide she's not going to have any potential energy, right? Because it's at the lowest point. So we could say that our potential energy is 0 right there, right? If you made that our reference point, our bottom point, our reference point for potential energy. So really all you're left with is there's some potential energy at the top and some kinetic at the bottom. All right, and we know that the masses are going to cancel out. So all we really have is gy is equal to 1/2 VA squared, right? Which gets us the exact same thing we had before. So we're solving for VA, we get the square root of 2GH. All right, and then we'll end up with the same answer. All right, so there's two different ways you could have went about this. You could have simplified it a lot earlier and made the equations a lot simpler. Okay. So the next section talks about reading a potential energy curve. Right, so we're looking at a graph that shows what the potential energy is at a specific place, not a time, but a specific place. We know that our potential energy is equal to negative work. We've seen, or the change in potential energy is equal to negative work. We also know that work is equal to force times a change in distance, right? This is, remember, work is equal to F dot D. So, since you have negative work, you'll have a negative F dot D basically there. So rearranging this equation, we get the force is equal to some incremental change, or the negative incremental change in potential energy, right? So when we take a derivative of something, we're just looking at how it changes with respect to something else. So in this case, we're looking at how the potential energy is changing with respect to its position, right? And in this case, dx. Okay, and this is we're talking about one dimension. So either falling straight up and down or going across in the x direction. All right, so our first graph here, it's a plot of the potential energy, U, so that's what we have on the y-axis, versus its position. All right, so at a certain position, what is its potential energy? All right, the plot of Ux, the potential energy function of a system containing a particle confined to move along the x-axis. There's no friction, so no mechanical energy, or so mechanical energy is conserved, right? So there's no loss of energy at any point. Well, if I wanted to look at what the force was, remember we have the relationship. As this potential energy is changing with respect to position, we get our force. So this actually shows what the slope of this graph is. Right? So the force is going to be the slope of your potential energy graph. All right, so when you have a very strong force, you notice right here at x1, and then you can see it changing as it goes through. Notice that as we're decreasing in our potential energy, we're actually increasing in force. So we have a positive force. That's because of this negative sign right here. All right, the plot of the force Fx acting on the particle derived from the potential energy plot by taking its slope at various points. So again, we're just looking at the slope and plotting it over here. All right, so how is this used? Well, we have a couple situations here. First, we can create a flat line that shows a given value of the total mechanical energy, EMEC, right? And we know that needs to be conserved. So if we said that the total mechanical energy is going to be 5 joules, the difference between the total energy and the potential energy is going to be your kinetic energy, right? Because if it's not potential, then it's going to be kinetic. So if we need a total of this, and I only have, let's say, this much potential, then the rest of this needs to be kinetic, right? Okay. And that kind of goes for each of them. Now, even up here, I mean, if this is our total amount of energy, and you have more potential, that means you must have some sort of negative kinetic, right, to get back down to here, to get back down to this total. Okay, so at this position, your kinetic energy is 0. So we're looking at this point right here. This is on our line of total mechanical energy. So at this specific point here, the kinetic energy is 0. And we're going to call this the turning point. The particle cannot go further to the left, right? Because it doesn't have any energy to do so. It would need negative kinetic energy to go to the left. At this point, the kinetic energy is greatest. The particle is moving the fastest. So down here, when you're furthest away from the from your mechanical energy line, and you notice our potential is going to be 0 at this point, that's when you're going to have the most kinetic energy, right? And that means the particle is going to be moving the fastest at this point. All right, in this last picture, for either of these three choices for mechanical energy, the particle is going to be trapped, which means it cannot escape left or right. So let's say I had a particle that only had this amount of energy, right? It doesn't have enough energy to go any more to the left. It doesn't have enough energy to go any more to the right. Same with this one. If I had a particle here, I would be stuck between these two bounds, right? I wouldn't be able to get past that. I don't have enough energy to do that, enough total mechanical energy to do that. And even here, right, it's going to be stuck here because even at this point, right, there's no kinetic energy. Right? Kinetic energy is equal to 0 here. So it's going to have potential, but it's not going to have any movement to it. So it's also going to be stuck. Okay. So the potential energy curve and equilibrium point. So this is a plot of the potential energy versus position, as we've seen before. Now, if we place an object at x is equal to 4, it is stuck there, right? If we place an object right here, oops, and that's all the energy it has, it cannot go anywhere because it doesn't have enough energy to either go to the left, and it doesn't have enough energy to go to the right. Cannot move it on its own because it would require some negative kinetic energy. Now, if we push it slightly to the left, a restoring force is going to appear that moves it back to x4. A particle at such a position is said to be in stable equilibrium, right? So again, at this point, even if you nudge it a little bit this way, you're going to have some restoring force pushing it back down this way, because look at what the slope of the line is, right? If I push it left, you're going to get a positive force, right? Let's go back a couple slides. Let's look at our equation. If I push it to the left, you're going to get a negative force, right? So it's going to, basically, you're going to add potential, so you're going to giving it a negative force. It's going to get pushed back. All right, and same way this way. If I push it this way, right, it's going to be pushed back down along this, basically back down to this original point. So that means it's going to be in stable equilibrium. Now, at any point to the right of x5, so if we go anywhere over here, the system's mechanical energy is equal to its potential, and so it must be stationary. The particle at such a point is called neutral equilibrium. Right, so if you had a particle anywhere over here, any position over here above x5, it's not going to have any kinetic energy, so it's just going to stop there, and that's going to be called neutral equilibrium. All right, and then the last type is at point at x3. So if we place an object right here at x3, the kinetic energy is going to be 0, because if you notice, the slope is changing from a positive slope to a negative slope. So there's not going to be any force acting on it right at that point. Now, if the particle is located exactly there, again, the force is equal to 0. However, if it's displaced even slightly in either direction, so if I just give it a little bit of a force this way, it's going to go down to the bottom here. If I give it a little bit of a nudge this way, it's going to go down to here. Right, so it's going to be displaced. This is going to be called an unstable equilibrium point. Okay. All right, so let's go ahead and do an example problem. A 2.0 kilogram particle moves along an x-axis in one-dimensional motion, while a conservative force along the x-axis acts on it. The potential energy, Ux, associated with the force is plotted in this figure. All right, so you can see this is our potential energy curve. That is, the particle were placed at any position between x is equal to 0 and x is equal to 7, it would have the plotted value of U, all right, whatever the potential energy is there. All right, so at x is equal to 6.5 meters, which is right here, the particle has velocity of v naught is equal to negative 4.0 meters a second. All right, from this figure, determine the particle's speed at x is equal to 4.5. So right here, we're trying to figure out what the particle's speed is. Okay, well first, we know that at 6.5 meters, the particle has the kinetic energy given as such. So we know that kinetic energy is equal to 1/2 mv squared. So that's equal to 1/2 times our mass, which is 2.0 kilograms, times our speed, which is given as -4, right? And that's just going to be squared. So that's 4 meters a second squared. So its kinetic energy is going to be 16 joules. That's over here at 6.5 meters. All right. Because the potential energy there is equal to 0, the mechanical energy is then just going to be, so our mechanical energy, we know is equal to our kinetic plus our potential. And that's just an equal 16.0 joules plus 0, because there's no potential. All right, so our total mechanical energy then is going to be 16 joules. Now, this value for mechanical energy is plotted as a horizontal line, as you can see here, right? The 16 joules is the most amount of mechanical energy that we could have. From the figure, we see that at x is equal to 4.5 meters, the potential energy is U1, which is 7 meters, right? So at this point, our potential energy at 4.5, our potential energy is going to be 7. So if I just want to know what the kinetic energy, this difference is, it's just going to be, kinetic energy is just going to be our total energy minus the potential. Right, so that's just going to be 16 joules minus the 7 joules of potential, which means we have 9 joules at this 4.5 position. Now, because k1 is equal to 1/2 mv squared, we can find that our velocity is simply going to be 3.0 meters a second. Right, I just took this equation and solved for velocity. All right, so our velocity is 3.0 meters a second then. All right, the next part of the question is asking, well, where is the particle's turning point located? All right, so because the kinetic energy, because K is the difference between the mechanical and the potential energy, we want the point where the plot of potential energy rises and meets this horizontal line. So we want to know what this point is right here. We're trying to find what this position is, right? We can't find that by just looking at the graph. So because the plot of potential energy is a straight line, we can just draw nested triangles as shown in the second figure. So you can see these nested triangles here that they kind of drew in. So we have this triangle, we also have this triangle, right? And they have the same ratios to each other. So to find what this distance is, or really what we're trying to find is this position here, we can just create a ratio. All right, so if we do the first triangle as 16 minus 7, right? It's going to be 16 minus 7 gets us this distance here, and we divide that by d, what we're calling d. Okay, we set that equal to the bigger triangle, so it's going to be 20 minus 7, and this distance here is going to be 4 minus 1. Oops, I'm sorry, 1 minus 4. 1 minus 4, 1.0. So this is going to be 1.0 minus 4.0. Okay. So that's going to, so if we just take this ratio and we solve for d, we find that our distance is 2.08 meters. But I don't really want to know what this distance is. I really want to know what this is, right? The actual, well, the distance away from 0, right? This distance here. All right, so that's just going to be, so our x value is going to be 4.0 meters minus whatever this distance we just found is, which is 2.8, or 2.08 rather. So that is going to be equal to 1.9 meters. All right, so the turning point is at 1.9 meters. This right here is going to be 1.9. Whoops. Okay, so the last point is evaluate the force acting on a particle when it is in the region 1.9 meters to 4.0 meters, right? So we're looking at this region here from this all the way to 4, right? What is this force? And in this region, we know that the slope is going to be constant, so the force is constant, right? Because we said the slope of the potential energy line is the force. Since we have a constant slope, we know that the force is going to be constant. Okay, so if we remember, our force is just equal to the slope of our, the slope of our potential energy, right? All right, and that's just really the change in potential energy over the change in distance. So we can sort of treat this as an integral when we look at see what the area under the curve is. Or excuse me, what the not the area of the curve, but what the changes are, and that would get us minus 20 joules, minus 7 joules, right? Because that's going to be this distance here, divided by what our change in distance is, which is this distance here, which we know is just going to be 1.0 meters minus 4.0 meters. We get a value of 4.3 newtons. All right, so that's going to be the force that's being applied to the object. All right, so the force has a magnitude of 4.3 newtons and its positive direction of the x-axis. This result is consistent with the fact that the initially leftward moving particle is stopped by the force and then sent rightward. Okay, that's it for this lecture. We will pick it up next time.